Okay, better. PRNG in cryptography can be used to generate random keys or for one-time cryptography. And a lot of research have shown that the existence of a PRNG is equivalent of the existence of one-way functions. That is function which is easy to compute but hard to invert. There are two families of PRNG. Those based on block cipher scheme in OFB mode, like iOS, and they are very fast. And the other, those proven as secure as a difficult problem. If we can build a distinguisher, we can break a difficult problem. So the problem can be factorization, district logarithm, or post-quantum problem based on linear algebra, like coding theory, like this multivariate quadratic polynomial system. Sorry. And for the PRNG we made, we made a PRNG based on the rank metric. We achieved to have a very small data size, only a few kilobits. Our PRNG is reasonably fast for PRNG based on coding theory. And it is asymptotically better than PRNG based on Hamming metric like RankSynd. And we also study the impact of a quantum computer against our algorithm. So now I will define the rank metric. First, we need to define what the matrix code is. A matrix code of length m times n is a code whose entries are a matrix of size m times n. And if C is of dimension k, we say it's an m times nk code. The difference between a matrix code and a code of length mn is that we can define the rank matrix over matrix code. And by definition, the distance between two words is the rank of their difference, and the weight of a word is its rank. A very interesting subfamily of matrix code are the FQM linear codes. So if we consider a vector with coordinates in an extension field FQM, we can associate a matrix of size m times n to this vector by writing each coordinate of the vector in a chosen basis. And by definition, the matrix code associated to FQM linear code of length n and dimension k is matrix code of length m times n and dimension km. The rank of a word of C is independent of the choice of the basis, and these two codes have the same distance, the same minimum distance. The advantage of FQM linear codes is that they need less bits to be represented. If we consider a parity check matrix of the two previous codes, for the FQM linear codes, we need k n minus k element of the extension, so k n minus k m log q bits to represent these codes. And for the matrix code, we need k n minus k m square log q bits. And this factor m we gained, thanks to the FQM linearity, allows us to reduce the size of the data for our generator and to have asymptotically better behavior. Now I will define the rank syndrome decoding. So it's very similar to the syndrome decoding in the Hamming metric. The difference is that the parity check matrix is over the extension field, and the syndrome too. Donc, so we need to compute a word with a given weight and a given syndrome. There is a probabilistic reduction to the syndrome decoding for the amic metric. So we can claim that the RSD problem is difficult, even if it is not proven NP complete. But if we for matrix code, if we yes, so just for matrix code, the problem is equivalent to min rank, which is NP complete. There are two types of attacks: the combinatorial attacks, which are more efficient when Q is small, which consists to find a subspace which contains the support of the error. The support of in rank metric, the support of the error is a subspace generated by the coordinates of the vector. And the algebraic attacks, which solve an algebraic systems by Grobner basis. There is several ways to choose the system, but overall, all these attacks have a complexity in 2 power n square. If we have all the parameters linear to n, and so if we have a fixed security parameter lambda, we have n proportional to the square of the square root of lambda. And since the code needs n cube bits to be described, we only need lambda power 1.5 bits to describe the code. And for ramming metrics, it's lambda square, if we don't add another additional structure like cyclicity. So we have a better asymptotic behavior for the size of the parameters. For quantum attacks, we can have a quadratic speedup to the combinatorial attacks thanks to the Groover algorithm. So basically, we need to double the security parameters against a quantum attacker. Okay, now I can describe how our generator works. So first, we need a family of one-way function. So we will use the hardness of the rank syndrome decoding problem to build this family. It's very simple. We have H, which is a parity check matrix of FQM linear code, and our function take a word of a rank weight omega n, and it computes its syndrome. And if we have omega n near the Gilbert-Overshamoff bounds of the code, then f is one way. So to produce a sequence, a pseudo-random sequence, we need that f expands the size of the input. So we choose omega n lesser than the DGV, and thus we obtain n square bits each time we use our one-way function. And the cost of the one-way function is a product matrix vector in the extension field, so it's n3 n cube operation in FQ. And then we need a function we can compute a word y of weight omega n. Remember, y can be seen as n times n matrix of rank omega n. So we can write m equal a times b, where b is a basis of the row space of m, and a is the coordinates of the row of m in this basis. This representation is not unique. We need to choose the matrix B in its echelon form to have the uniqueness, but it's hard to compute all the echelon matrix. So we use the same idea as in SYND. We only compute a proportion of word of weight omega n by choosing B of the form identity and matrix. So in total, for the matrix B, we need n square omega minus omega square log qubits, and for A, omega n square log qubits, which is exactly the number of bits we have at the beginning. The question is the rank syndrome decoding problem as hard for regular words as for random words? And the response is yes, because the proportion of regular words is always greater than a constant for all q and all n. This is because if we see this representation of M, Y is a regular word if the square matrix of size omega n, which is the omega n first columns of the matrix B, is invertible. And the probability that this matrix is invertible is always greater than a constant. So now we have our one-way function and our expansion function. We can build our generators. On input, we have k bit, where k is the security parameter, a parity check matrix, and an initialization vector. Sorry. First, we compute a word of weight omega n. We compute its syndrome, and we split its syndrome in two strings. One of length n square 2 omega minus omega square log q to after compute another y, and we output S2. And we do that until we have enough bits generated. So it's a very simple algorithm. So how can you prove the security? For that, we will demonstrate that we can build a distinguisher for the Fisher-Stern PRNG if we have a distinguisher for all generators. And the Fisher-Stern PRNG is based on the rank on the syndrome matrix decoding in the Hamming metric, and it's very similar to all generators. It takes in entries a vector of weight d, where d is below the Gilbert-Bachamov distance for the matrix code, and it computes its syndrome. And it repeats the processus exactly as we do. It's our generator which do the same thing than the Fisher-Stern PRNG. And to build the distinguisher for the Fisher-Stern PRNG, we need to embed a FQ linear code into a FQM linear code. To do that, we choose an n-tuple of FQM, and we define a function psi alpha, which computes the star product of alpha with a vector of FQN. And if C is a linear code over FQ, the code C alpha, we denote the code C alpha, the FQM linear code generated by all the world of the world C alpha of C. So the property of the C alpha codes is if the coordinates of alpha are FQ independent, then the rank weight of psi alpha of x is equal to the Hamming weight of x for all x in the code C. And if D is the minimum distance of C, then if we choose M greater than 8n, we can typically the minimum rank distance of C alpha will be D. And so with these two properties, we can build our distinguisher. So if our generator is not pseudo-random, then we have a distinguisher for all generators. And to build the distinguisher for the Fisher-Stan PRNG, we take as input M and S. So M is a matrix, a parity check matrix for an Hamming code, and S can be either a syndrome or just a random vector. We chose alpha in the extension field with its coordinate F2 in linearly independent. We give to dr the input psi alpha m and s, and we return the same value as dr. So if s is a syndrome of a world of weight of Hamming weight d, then s is also equal to psi alpha m psi beta x, where beta is the invert of alpha. And according to the properties of the embedded code, we can see that the rank weight of psi beta x is also d. So dr will accept the entry psi alpha ms with a non-negligible advantage. And if s is random, dr outputs 1 with probability 1.5. So there is a difference between if there is an advantage if S is a syndrome for the Fisher-Stan from the Fisher-Stan generator than if S is random, and that's how our generator works, or the distinguisher works. Sorry. Now I will talk about the parameter of our algorithm. So first, I will talk about the asymptotic behavior. In the case m equal n and h random, the cost of the syndrome is n cube operations in the base field, and it outputs n square random bits. So the number of operations per bit is linear in n. And the complexity of the best attacks is in 2 power n squared. So the cost per bit is proportional to the square root of lambda, where lambda is the security parameters. And in the Hamming matrix, it's proportional to lambda if we don't add any additional structures. So asymptotically, our generator is faster. And it's also smaller data size, thanks to for the same reasons. So we give two sets of parameters. One, we try to optimize the size of the data. So if as you can see, we have only a few kilobits, but it's rather slow. And we also give parameters for quantum attack. It's the last rows. And on the other hand, we can optimize the speed. And here we are still slower than the iOS, but we have a speed which are very comparable to what it's done with SYND. And we have data size which very smaller than SYND if we don't add any structure. So in conclusion, we propose a PRNG proven as secure as the rank syndrome decoding. We have good result in terms of data size and speed. And we have also studied the impact of quantum attack and give quantum resistant parameters for our generators. Thank you for your attention.
Thank you, Adrien. We have time for questions.
Finally, I have two questions. So the
Yes.
first question is about your security bonds that you obtain for algebraic attack.
Hmm?
How do you obtain the n square?
It's because if we have if we if the systems if the unknown of the system are in the base field, we have m times w unknowns, so it's quadratic in n. So the number of unknowns is quadratic is n. That's why the
It's quadratic in
n. N. Sorry, n.
So my second question is how this compare to quad? So quad is a string site.
Kind of the same technique, but which is based on the hardness of solving a random system.
We don't really compare quad and our generator because we wanted to compare in the field of coding theory. So I don't know how fast quad is. Sorry.
Are there other questions? No?
So your security proof, how does the complexity of attack suggested by best known attack compare to the limit based on the security proof and the best known attacks on the Stern generator?
Sorry, I don't understand.
So you have a security reduction proof.
Yes.
To a different generator, correct?
Yes. Yes.
So if you estimate the attack complexity based on what you've proven through your security reduction proof, how does that compare to best known attack? How tight is the reduction?
Yes, I see what you want. I don't really know how you want to see if we have an attack on the Fisher-Stern generator, we can attack all generators. I'm not.
Well, right, so the question is you've reduced the complexity of attacking the Fisher-Stern generator. So if you set the security parameter based on the best known attack.
Yes, but I think yes, I understand. I think the direct attack on the rank syndrome problem are faster, are more efficient than an attack on Stern on the Fisher-Stern generator applied to our generators. I think.
We still have time if there are more questions.
I have a question. So I cannot understand your reduction because in your reduction, please let me see your reduction security proof. Yeah. So I guess the psi alpha of m contains the several zeros because m about half of m is 0.
Oh, sorry.
Sorry. So you embed the capital M into another random matrix by using this psi alpha. Yeah. So therefore, the matrix M contains 0 about half, because M is random matrix in the Fisher-Stern generator, isn't it?
Sorry, I don't understand the question.
I think so. You embed the capital M of Fisher-Stern generator to your matrix H by using this function. But so this function changes the distribution input to the reduction, so your distinguisher, D of R. So therefore, so I wonder how you show the distribution of the distribution of the psi alpha of M. It's correct or not? Okay,
Sorry,
so let me ask after.
I don't know.
Okay, so let me ask after the session.
Okay.
Okay, anything else? No? Well, if not, then let's thank Adrien and two speakers of the session again.